Okay, today we derived the Reynolds transport theorem, which allows us to convert a description of dynamics or movement or transport from one reference frame to another. The idea here is to be able to go from a moving frame, which is following a system of particles, and so if we think of a system of particles being flagged by red dye, say, and that system of particles is moving with the flow, and it's easy to illustrate in a channel here, but it holds more generally. And then it passes through a virtual control volume. And the control volume will denote by CV, that's a V, and the system will be denoted by SYS. We then define B to be some fluid characteristic. It could be mass, it could be momentum, and then beta is that characteristic per mass of fluid, B over M. Now, the Reynolds transport theorem can be derived really just as a bookkeeping exercise where we keep track of what enters and exits the control volume. The result is the following, that the time rate of change of our characteristic of the system of particles is equal to the time rate of change of the characteristic of the control volume, as long as we account for the fluxes into and out of our control volume. And the way we can do that is by integrating over the control surface, where the control surface is the bounding surface of the control volume, of the fluxes through those faces carrying quantity beta. And so we think of rho beta times V dot dA. Okay. Now, the way to think about this is V dot dA is the volume of fluid crossing the control surface per time. If you multiply that by rho, so that means that rho V dot dA, rho of course is mass per volume, and it's times volumes per time. This is mass per time crossing the control surface. So when we multiply by beta, rho beta V dot A dA is the amount of B crossing the control surface per time. So when you add that up over the whole volume, you get something that relates to the change in B in the control volume. Now what we're going to do in coming lectures is we're going to say that we have a conservation law that describes the rate of change of some characteristic. This is a reference frame following the fluid parcels. And we're going to use this to convert it to a reference frame that is fixed and the fluid passes by. The reference frame following the parcels is the Lagrangian frame. The reference frame that the fluid is passing through would be known as an Eulerian frame. It's the Eulerian frame that we want to be able to use in our analysis, but our conservation laws are written in the Lagrangian frame, and so the Reynolds transport theorem allows us to connect one to the other.